Welcome to Lecture 2.3, Equivalence and Implication. One way to think about equivalence is that it is to logic as equality is to algebra. Formally, propositions R and S generated by a set capital S are equivalent if and only if the biconditional operator applied to them is a tautology. We denote this using the biconditional operator but with a double arrow instead of just a single arrow. So we say R is equivalent to S. The following are all examples of equivalences. First, P and Q, or not P and Q, is equivalent to Q. And recall that to show this, we have to show that these things have the same truth table, which is what the biconditional operator means. And if you pause this and wrap your head around what this says, then it should hopefully make sense that the value of P doesn't matter, sort of by symmetry. Let's check this just to make sure. So here's P and Q. Here's the truth table. So we have 0, 0, 0, 1, 1, 0, 1, 1. And now I'm going to use red for the other entries. So P and Q, I'll just put that down here. That's going to be 0, 0, 0, 1. And then not P and Q is going to be 0, 1, 0, 0. And so if we're going to OR these things together, then we're going to get 0, 1, 0, 1. And notice that the values where they take 1 is just the same as when Q takes 1. So that's why these two things are equivalent. Okay, so moving on. P implies Q is equivalent to not Q implies not P. P or Q is equivalent to Q or P. Every tautology is equivalent to the constant function 1, that is where every input gives true, and every contradiction is equivalent to the constant function 0, where every input gives false. Though it is convenient to use operations such as the OR symbol or the conditional or biconditional operations, they are technically unnecessary. All three of these can be achieved using just an and not symbol. So let's just see this with an example. So here's a truth table. Here are the inputs for P and Q. Of course, P or Q, reading down from the truth table, is 0, 1, 1, 1. And that truth table is the same as this one, which is the negation of not P and not Q. So let's check why this is. So the inside of this, not P and not Q, is only going to be true when P and Q are 0. So we have 1, 0, 0, 0, and then the negation of that just flips the bits, which gives us this. So anytime that we have a Boolean expression and we have a not or an OR symbol, P or Q, we can always just replace that with this expression involving negations and ands. So we never actually need to use an OR symbol if we don't want to. Okay, next, the biconditional operation. Its truth table, as we've seen, reading from top to bottom, is 1, 1, 0, 1. And as we've also seen, that can be expressed as not P or Q. Now that, along with the equivalence we've seen right here, means that we can write this as not, the negation of not P and not Q, or equivalently, the negation of P and not Q. Next up, the biconditional operator, which is 1, 0, 0, 1, going down the truth table, is equivalent to P and Q or not P and not Q. Let's see why. Notice that P and Q takes the value of 1 precisely when inputs P and Q are both 1. And not P and not Q takes the value of 1 precisely when the inputs P and Q are both 0. So if we union these together, we get a truth table that has two outputs of 1, which are these two entries right here. Okay, so in summary, anytime we have a Boolean expression involving an or, a conditional or biconditional operation, we can eliminate those and write the whole thing involving and not. It's not too hard to see that we actually need both of these operations, that one of them alone will not suffice. So we can't get rid of and because negation is just a unitary operation, has one input. And it's not too hard to see that you can't write everything with just ands as well. But perhaps surprisingly, we can actually generate every Boolean function using just one operation. It's just not either of these operations. Either of the following will suffice. Let me give them to you in truth table form first. So the first one is P with this vertical bar Q, and the outputs are 1, 1, 1, 0. And the next one is P down arrow Q, and the outputs are 1, 0, 0, 0. This vertical bar is called a Sheffer stroke, and this down arrow is called a Pierce arrow. So before I show you a more common name for these two things, we don't usually use these symbols or these names, let me motivate where these are coming from. So first of all, this should be pretty surprising, because if you compare the truth table for this first one, it's almost the same thing as the truth table for the AND operation, just upside down. So it seems like, well, if one of these should suffice to write all Boolean functions, then the other one should as well. But that's actually not the case. And now let me compare the second operation. So the second operation, the Pierce arrow, to this one up here, notice that that is actually the negation of it. So this is sometimes called not and, so N-A-N-D, Q, because it literally is the negation of the and operation. And similarly, this thing here you might now recognize as the negation of the or operation. So we'll call that one not or just nor for short. In summary, the function P vertical bar Q is also called NAND, short for not and, because it is equivalent to the negation of P and Q. And the function P down arrow Q, the Pierce arrow, is also called NOR, short for not or, because it is equivalent to the negation of P or Q. Let's check this with the truth tables again. So P and Q has truth table 0, 0, 0, 1. And so the Sheffer stroke, or the NAND function, is just the negation 1, 1, 1, 0. Similarly, P or Q has truth table reading top to bottom 0, 1, 1, 1. And the Pierce arrow, or the NOR function, is the negation with output values 1, 0, 0, 0. The NAND and NOR operations are said to be universal because, as I said earlier, either one of them can generate all Boolean functions. To verify this, all we have to do is just check that both of them can individually generate the NOT operation and the AND function as well, because we know that those two things, AND and NOT, can generate everything. So let's check this. So first of all, let's draw a truth table. There's only two inputs for one variable, P, 0, and 1. Not P, we get 1, 0. And then P NAND P, when P is 0, well, we just get the value 1. 0 NAND 0 is 1. And 1 NAND 0 is 0. And so here we see that these two things are equivalent. And we get the same thing for NOR, because notice that when P is 0, P NOR P is 0 NOR 0, which is 1. And when P is 1, 1 NOR 1 is equal to 0. So both of these are clearly equivalent to just not P. Next, we need to show that Nand and NOR can generate the AND operation. And I'm not going to check this with the truth table, but I encourage you to pause the lecture and verify for yourself that if we take the NAND function of P NAND Q with P NAND Q with itself, then that gives us the same truth table as P and Q. And similarly, if we take the NOR function, this is a little bit different, of P NOR P with Q NOR Q, then we get the same truth table as P and Q. Finally, we don't need to do this, but it's worth mentioning that the OR function can also be written in a very similar manner as the AND function, but in some way this is dual, where these expressions are switched. And by that I mean P or Q is equivalent to the NAND function of P NAND P with Q NAND Q. So notice the P's and the Q's like we had up here. Or if we want to use NOR, we get the NOR function of P NOR Q with P NOR Q. And that looks a lot like what we had up here. At this time, I want to show you some basic logical equivalences. Now, most logical equivalence, however complicated it may be, can typically be deduced by applying a few basic logic laws that I will show you below. Each of the following laws has a so-called dual law, which is obtained by exchanging the following symbols, and an OR, and 0 with 1. Let me show you some examples. We'll start with a law that we refer to as commutativity, which just means order doesn't matter. So one version of this says that P or Q is equivalent to Q or P. I don't think I need to convince you why these have the same truth tables. And the so-called dual law is obtained by replacing these OR symbols with AND symbols to get that P and Q is equivalent to Q and P. Next, we have associativity, which means that parentheses, if we're not mixing ANDs and ORs, are permitted anywhere and required nowhere. So, said differently, P or Q or R is equivalent to P or Q or R. And the dual law is P and Q and R is equivalent to P and Q and R. Next is the distributive law, which you're probably familiar with from basic arithmetic or algebra, which says that P and Q or R is equivalent to P and Q or P and R. Or dually, P or Q and R is equivalent to P or Q and P or R. Now this is sometimes called the left distributive law because notice that there's some symmetry here. I'm sometimes multiplying P on the left of this expression, and there is also an analogous right distributive law, which I'm not going to write down, but I will encourage you to pause the video and figure it out for yourself if you don't already see what it is right away. Next is the identity law, which says that P or 0 is equivalent to P. This makes sense. If you're taking the conjunction of any proposition with something that is never true, then you just get that proposition. The dual law, this is the first one that we replace an OR with an AND, but also a 0 with a 1, is that P and 1 is equivalent to P. And that should make sense too, because if we need both of these things to be true, and the second one is always true, then we can just ignore it, and this is true precisely when P is true. The next law is sometimes referred to as negation. I know it's a bad name, not to be confused with the negation symbol that we have right here, but this says that P and not P is a contradiction. This is always false. These things both can't be true at the same time. And the dual law says that P or not P is equivalent to 1. That is a tautology. It's always the case that P is either true or false. Next we have the idempotent law, which just says that P or P is equivalent to P. And the dual law says that P and P is equivalent to P as well. Next, we have the null law, which is in some sense similar to the identity law. So here we had P or 0 is equivalent to P, and if we change this or into an and symbol, then we get a different result, but we get P and 0 is equivalent to 0. And that should make sense, that if we take the and function of any clause and something that's never true, then we can never get anything true. It's always false, always a contradiction. And dually, if we take P or something that's always true, we get something that's always true. That is a tautology. Next up, we have the absorption laws. The first one is P and P or Q is equivalent to P. Maybe this is not quite as obvious as some of the previous ones, but let's check it out anyways. So P can take two values, 0 or 1, and P or Q, well, if P is 0, then this is going to be, I don't know, 0 or 1 of the two, we don't know, depends on Q. But in either case, if we take 0 and either value, we are going to get 0. And if P is 1, then P or Q is going to be 1, and 1 and 1 gives 1. So in both of these cases, the output value is precisely just the value of P. So dually, we have P or P and Q is equivalent to P. Let's check that out. So if P is 0, then P and Q is going to be 0, and 0 or 0 is going to be 0. But if P is 1, then P and Q is going to be 0 or 1, we're not sure. And if we take the or function, 1 with anything is going to give us 1. So once again, the output is going to be just what P is. Next up are De Morgan's laws. The first one is not P or Q is equivalent to not P and not Q. And the next one is not P and Q is equivalent to not P or not Q. This is probably best understood with examples. So let's do one in plain English. So if I say that I did not go to the park or the beach today, then you can conclude that I did not go to the park and I did not go to the beach. Similarly, or dually, if I say that I did not eat breakfast and lunch today, then you can conclude that either I did not eat breakfast or I did not eat lunch. So far, we have focused our attention on the first topic in the title of this lecture, that is equivalence, and now we will turn our attention to the second topic, that is implication. And we will motivate this with an example. Suppose you were told that one of the two propositions is true and the other is false. So first, X says that the money is behind door A, and Y says the money is behind door A or door B. One of the two, at least one of the two. Which door would you choose? Well, hopefully you can see right away that door B has got to be where the money is. If you don't, let's go back and do this in slow motion, or break it down. So if X is true, if the money is behind door A, then it must be true that the money is behind door A or door B. That's certainly not false. So if X is true, then Y has to be true. But the converse need not hold. So if Y is true, if the money is behind door A or door B, we can't necessarily conclude that it is behind door A. We just don't know. So it's not necessarily going to hold. But once I tell you that one of these is true and one is false, we know that X cannot be true. Because if X is true, then they both have to be true. So the only possibility is that X is false, and that would force Y to be true by default. And that would mean that the money is behind door B. To formalize this, let capital S be a set of propositions, and let lowercase r and s be generated by this set. We say that R implies S if the implication, if R then S, is a tautology. And as before, we denote this with that same implication symbol, but just with a double arrow instead of a single arrow. So we write R implies S. Let's do an example. Well, the following implication, P implies P or Q, is called disjunctive addition. This is basically what we saw above. So if P is true, then it is certainly true that P or Q are true. So if the money is behind door A, then the money is definitely behind door A or door B. But let's just check it out in terms of truth tables as well, because we've seen cases where sometimes truth tables can be a little bit misleading or counterintuitive, especially P implies Q. It wasn't clear right away maybe that any input value of 0 has to lead to a truth value for if P then Q. Okay, so here are the inputs for P and Q. P implies Q is 1, 1, 0, 1, and P or Q is 0, 1, 1, 1. Now we just have to check that the conditional operator, if P then P or Q, is a tautology. So the input here is P, that's this column, and the right-hand side is P or Q. So in each of these cases we have if 0, then 0. So 0 implies 0, that is indeed P, well, let's write this over here. That is indeed 1. Similarly, if P is 0 and P or Q is 0, 0 implies 1. That is also true. And 1 implies 1 is true, and 1 implies 1 is true, and so that is indeed a tautology. Here it is cleaned up, and because this is a tautology, in other words, all 1s in the truth table, we say that P implies P or Q. Earlier in this lecture, we saw some basic logical equivalences, and now we will see some basic logical implications. The first one, sometimes called detachment, and this says that if P then Q is true and P is true, then that implies that Q is true. And hopefully that should make intuitive sense. Next we have indirect reasoning, which says if P then Q and Q is false, then P has to be false. We have disjunctive addition, which we just saw. P implies P or Q. Next, we have conjunctive simplification. This says that P and Q implies P. So that should make sense. If P and Q both have to be true, then certainly P individually has to be true. And also P implies Q for the same reason. And finally, disjunctive simplification says that if P or Q is true and P is not true, then Q has to be true. And similarly, if P or Q is true but Q is false, then P has to be false. So I'm not going to go over these with truth tables, but I encourage you to do the same thing that I did in the previous slide, to actually, for each one of these explicitly, let me just show you right here, find the truth table, or write down the truth table for P or Q, and not P, and take the conditional operator with that and Q, and check that that is indeed a tautology. So check with P and Q that all 4 inputs in fact lead to 1, 1, 1, 1. The detachment law, the first one above, is often called Modus Ponens, which is short for Modus Pudendo Ponens, which is Latin for mode that affirms by affirming. It actually dates all the way back to the ancient Greek philosopher Theophrastus, who lived from 371 to 287 BC, and he was the one who succeeded the founder, Aristotle, of the peripatetic school. Similarly, the indirect reasoning law above, this one, is often called Modus Tollens, short for Modus tollendo tollens, which is Latin for mode that denies by denying. Now I'm going to list a few equivalences involving the conditional operator that we have seen before, although the first one is actually not an equivalence, it's an implication. It's transitivity. You probably know it just from everyday life. It says that if P implies Q and Q implies R, then that proposition implies P implies R. Now notice I've used implies in two slightly different contexts, one of them to describe the conditional operator, but also to describe implication, as we defined it formally earlier. Next up, something that we saw a few slides ago, conditional equivalence. P implies Q is equivalent to not P or Q. We also saw biconditional equivalence, which says that P if and only if Q is equivalent to, well, here's what we saw, P and Q, or not P or not Q. But I also claim that those are both equivalent to this third one here, P implies Q and Q implies P. Let's just check that really quickly. P, Q, 0, 0, 0, 1, 1, 0, 1, 1. We know that P implies Q is only false when 1 implies 0. We know that because that's not true. So otherwise, it's ones. And similarly, Q implies P is going to look like this. And so if you AND these things together, you get 1 precisely when either both Q and P are 0, or both of them are 1. Finally, the contrapositive we've seen, P implies Q is equivalent to not Q implies not P. At this point, I'm going to pause and stress the importance of language, because as you know, sometimes language can be misleading, and other times phrasing a logical statement slightly differently can make it less or more clear, or sometimes unintentionally change the meaning. Let me give you an example. Consider the following two statements. First, if Alice or Barb go, then Chris will go. Next, if Alice will go, Chris will go, or if Barb will go, then Chris will go. Are these equivalent? And if not, does one of them imply the other? So as we would say these in everyday conversation, it sounds like these should be equivalent. We're basically saying that Chris likes these two girls, Alice and Barb, and if either, it sounds like if they go, presumably to the dance or some event or party, then Chris will as well. However, if we actually draw out truth tables, we will see that these will be slightly different. So let's check that. So let's say that A is true if Alice goes. B is true if Barb goes. And C is true if Chris goes. Okay, so let's do A, B. Let me then do A or B. Let me put a C in there. And I will continue this in a bit. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so I'm going to add some extra lines in here just so we can keep this straight. No pun intended. These aren't very straight lines anyways. Okay, so A or B, let's see, so 0, 0, 1, 1, 1, 1, 1, 1. So now let's do A or B implies C. Okay, so we have these two columns here. So all of these will be true unless the left column is 1 and the right column is 0. So we're going to get 3 zeros, those are right here, and the rest of these are going to be 1s. And then, let's see, the next one is, that I'm going to do is A implies C, and then I will do B implies C, and then let me do A implies C or B implies C. So there's this first statement, if Alice or Barb go, then Chris will go. That's this first one right here. So let me circle that, or box that. And then the next statement, if Alice will go, Chris will go, or if Barb will go, then Chris will go, is this second statement right here. Okay, so let's keep going. So A implies C, so this is going to be 1 in all entries except when A is 1 and C is 0. So let's see where that happens first. So we have this entry right here, and we have this entry right here, and all of the other ones are going to be 1s. And similarly, B implies C is going to be 1s everywhere except where B is a 1 and C is 0. So that's going to be in this entry and that entry. So let's do those first. So this is going to be a 0. Let me find my pen. This is going to be a 0. And the other one, where was it? It was down. B implies C is going to be 0 as well, and the rest are going to be 1s. Okay, so now let's take the disjunction of these two columns, and what we get is we get 1, 1 is, well, we get 1s everywhere except in this one case. Okay, so let's interpret that. So first of all, these are definitely not equivalent because they have different truth tables. However, is it true that if one of these holds, then the other one holds? So if this first one has a 1 in a certain position in the truth table, then this second statement also has a 1 in that position in the truth table. So therefore, we can say that 1 implies 2. So does 1 imply the other? Yes, 1 implies 2. Anytime 1 is true, 2 is true as well. So let's just finish by looking at where these things differ. So both of these, this seventh line is false. So if Alice and Barb both go and Chris doesn't go, then yes, that contradicts, or that goes against these statements. But this first statement, if Alice or Barb go, then Chris will go. These things have a false implication if in the case when Barb goes but Alice does not, or Alice goes and Barb does not. So that's a little bit counterintuitive because the human being who is saying this is probably implying that if Barb goes, only Barb, or if only Alice goes, then Chris will go. But logically, this is different from the second statement, which is a little more cumbersome, but most humans are probably going to say seems equivalent. If Alice will go, Chris will go, or if Barb will go, then Chris will go. So just a word of warning, many times in logic, if you say out a statement in plain English, it's exactly what you think it is in terms of equivalence and implication and so forth. But other times like this, there are subtle differences. In other words, language can and will be misleading. Here's our next example. Consider the following two statements. First, if you get 90% in this class or an A in the final exam, then you'll get an A in the class. Now, suppose that I'm planning on putting at least one of the following statements on the syllabus. First, if you get 90% in the class, then you'll get an A. And second, if you get an A in the final, then you'll get an A. Are these equivalent? And if not, does one imply the other? So first of all, what do I mean when I say I'm putting these statements on the syllabus? At least one. Let's say that I'm putting both of them. And so probably what I would say is this first one, if I get 90% in the class, by the way, let me call that an A, then I'll get an A in the class. Let me call that C. So this says A implies C. And then an A in the final, let's call that a B. I'm sorry that I'm double using A for a grade and also a proposition. And then the second one says if you get an A in the final, so this is B implies C. So really what I'm saying is, well, this is how you can get an A in the class, or this is how you can get an A in the class this way. So notice this is exactly the same logically, as I've written it here with this or, as this example 1. But I'm doing this example because I find it a little bit more intuitive to understand when we have a guarantee like this, which is, I guess if you think about how I introduced this in a much earlier lecture, when you first saw the conditional operation, it wasn't clear why 0 implied 1 was true, but 1 implied 0 was false. And the best way to think of it, I thought, was this example. If you get a 90 in the class, you get an A. So if you don't get a 90 in the class and you get an A, I haven't broken my promise. But if you get a 90 in the class and you don't get an A, I have broken my promise. So for me, that was more intuitive. And so that's why I'm going to go back to this example to explain this as well. So I'm not going to rewrite the whole truth table, but I will rewrite the truth table in the 2 entries where these things differed in example 1, if you remember, and then we'll try to understand what was going on. So A, B, A or B, C, A or B implies C, and then A implies C, or B implies C. Okay, so let me do, so let's see, 0, 1, 1, 0, and 1, 0, 1, 0, and 1, 1, 1, 0. So in all 3 of these cases, this is where we got zeros. So if A is false but B is true, then A or B, 1 implies 0 is false. And similarly, if we switch A and B, and if they're both true, then we get 1 implies 0 is false as well. Now over here, A implies C. Suppose, so in this case, 0 implies 0 is true, 1, but B implies C is false. This is switched, 0, 1, and now we have A implies C is 0, 0. So if we OR these together, I'm going to cheat a little bit and say this is 1, 1, 0. So this is where these things differed in the truth table. Well, actually, only in 2 of these entries. This was the only 0 entry, if you remember, in example 1, this case. So let's try to understand what's going on and why these things differ and how to resolve it. Not just here, but back in example 1. So these 3 zeros come from the fact that I have broken guarantees. If you get an A in the final, but maybe not a 90 in the class, and you don't get an A in the class, I've broken my promise. If you get a 90 in the class, and maybe something not good in the final, but still a 90, and not an A, I've broken my promise. If you get both of these well, and you don't get an A, I've broken my promise. However, over here, what does this mean? So suppose I break my promise on this first, or no, I'm sorry, suppose I keep my promise here that 90 in the class gets you an A in the class, but a few people get an A in the final but don't get an A in the class, I have broken my promise. But how I've phrased it, what this is actually logically saying is that, well, I've kept at least one of my promises. Similarly, I've kept at least one of my promises, so it returns true. But if I broke both of these promises, then indeed it returns 0. So how do we reconcile this? So really, what I can do to make this equal to that is instead of ORing these together, ANDing these together. So let me do that. Let me change this to an AND, and that will change this to 0, 0, 0. And now these are the same. And let's look back at what happens down here. Well, here I said OR, because that's probably how I would phrase it in plain English. I would say, if you get a 90 in the class, you get an A, or if you get an A in the final, you'll get a B. Really what I should say is this is a policy. This is a policy, and this next one is also a policy as well. So if I were being a logician, that's how I would say that. And now we can go back up to example 1 and say, this or was the problem. If I should say, so if I make this or an and, so I say, if Alice will go, Chris will go is a true statement. And if Barb will go, then Chris will go is a true statement. Then that actually will fix the truth table, make these things equivalent. But that said, in this case, and or, in terms of plain English, are almost interchangeable. We say the same thing to mean the same thing, but really and or logically are different. So that really boils down to the importance of language. Sometimes language can be misleading. Sometimes what we say in our everyday life does not exactly match the logical meaning of the words, especially involving and or. Okay, so it's something that's worth being aware of going forward. Let's summarize what we've learned in this lecture so far. So in terms of truth tables, tautology means the truth table has all ones. That's actually from the previous lecture. As is the following. Contradiction means the truth table has all zeros. But now I want to tie this into equivalence. When I write P is equivalent to Q, that means P and Q have the same truth table. And implication, if P implies Q, that means that all of the ones in P's truth table are also in Q's truth table. So anytime P is true, Q must be true, but not necessarily vice versa. And also, it's not necessarily true that anytime P is false, Q is false. We also learned about the Nand and NOR operations, which are universal because they can generate any Boolean operation or Boolean function. This means that every digital circuit can be constructed only with using NAND gates or only NOR gates. For fun, here's a picture of an actual digital circuit made by Texas Instruments. I think I found this on Wikipedia. It is built up with 4 NAND gates. Okay, so that concludes this and the previous few lectures. Our introduction to propositional logic. And what we will do next time is we will take the logic that we have developed and possibly add a few more laws, which basic laws that we call axioms. We can't prove, they're just truths. Think of like axioms of geometry or axioms of arithmetic. And we will use those to build new universes and see what we can prove within those systems. So I hope you stick around for that.